Hello friends, I welcome you in lecture number 20 on group theory. In this lecture we will discuss one question on finding left cosets of a subgroup, and this question was asked in GTU Summer 2020 exam for 4 marks. So the question is, let Z with addition be a group where Z is the set of integers, and this plus sign is the operation of addition, that is standard addition. Let capital H be a subgroup of Z consisting of multiples of 5, that is capital H is subgroup of Z, which we can write as 5Z, and elements are multiples of 5, so we can write in this way 5n, where n belongs to Z. So we have to consider all the integer multiples of 5, and this H is a subgroup of set of integers under addition, and we are asked to find the left cosets of this subgroup H in the set of integers. The same question can be asked in this way also. Find the left cosets of H equal to 5 times Z in a group G equal to Z with addition. We have seen how to find out left cosets in earlier 2 lectures, and we just recall the definition of left coset. Suppose H is a subgroup of G, then for every element A of G, the left coset of H is denoted by A times H, and it is set consisting of this type of elements A star H, where H belongs to H. And we have seen certain properties also, that suppose this element A is present in subgroup also, then left coset corresponding to this element will be subgroup itself. And we have seen this another property also. Suppose A1 is a member of left coset A2H, then left cosets corresponding to A1 and A2 are always equal. Also, the number of elements in any left coset will be equal to number of elements in the subgroup. In the case of finite group, here we have infinite group, so we are not concerned about this result. But if we have finite group, that is group of having finite number of elements, then we can check this number of elements in any left coset will be equal to number of elements in the subgroup, and we will use these properties also to minimize our calculations or to save our time. So with this in mind, we try to find out left cosets of this subgroup 5Z in a group of integers. So first we write down our group is set of integers, that we can write in set notation in this way: 0, 1, 2, 3, 4, 5, 6 and so on. And here we have negative integers -1, -2, -3, -4, -5 and so on. And for each element of this group we have to decide left cosets. So, and we also write our subgroup H is set of integer multiples of 5, that is 5 times n, where n belongs to Z. Or in set notation we can write, suppose we multiply by 0, we have 0. If we take n equal to 1, it is 5. For n equal to 2, it is 10, then 15, then 5 into 4, 20 and so on. And similarly here, if we take n equal to -1, we have -5. For n equal to -2, -10, -15 and so on. Now we start by n equal to 0 or a equal to 0. We have to find out left cosets for every element of the group. Here group is set of integers, So first we take a equal to 0 and the operation is addition operation. So for a equal to 0, our left coset will be denoted by 0h, and because operation is addition, we can write this as 0 plus h also. Now if we observe that this 0 is present in subgroup, so we can directly write that this left coset will be equal to subgroup itself because 0 is present in H. Now we take a equal to 1, that is 1 times H, that we can rewrite in another notation as 1 plus H. Now 1 is not present here, so we use the definition of left coset. By definition we have to collect elements of this type 1 plus H, where H is a member of subgroup H. Now members of subgroup H are in this form: 1 plus 5n, where n is any integer. So for different values of n, we can write different elements here. Suppose we start with n equal to 0, we will have 0 plus 1, that is 1. For n equal to 0, element is 1. For n equal to 1, we will have 6. For n equal to 2, we will have 5 into 2, 10 plus 1, that is 11. And we can see the difference here. This gap is 5. 11 minus 6 is 5. 6 minus 1 is 5. So we can directly write down the next element by adding 5 to 11, that is 16. And that will correspond to n equal to 3. 5 into 3, 15 plus 1, that is 16. Similarly, suppose I take n equal to minus 1, I will have minus 5 plus 4, that is minus 4. Or we can write this minus 4 by subtracting 5 from its succeeding element, that is 1. If I want to write down element which is before this element 1, I will subtract 5, that is minus 4. And if I want to write down the element after 1, I will add 5, so I will write 6 here. So you can see this 6 is obtained by adding 5 to 1, minus 4 is obtained by subtracting 5 from 1. Similarly, next element will be minus 4 minus 5, that is minus 9, and that will correspond to n equal to minus 2. Similarly, for n equal to minus 3, we will have minus 14, and so on. This is infinite set. Or we can directly write these elements by adding 1 to each of these elements, that is 0 plus 1, 1, 5 plus 1, 6, 10 plus 1, 11, 15 plus 1, 16, and here also minus 5 plus 1, minus 4, and so on. So these are different ways of writing the same set, 1 plus h, where h belongs to h. Okay, fine. Now we find the coset corresponding to element 2. So now I am writing 2h. 2h, that is 2 plus h. So here elements will be 2 plus h, where h is a member of subgroup H. Now members of subgroup H are multiples of 5, so here we write 5n, n is any integer. So for different values of n, we will have different elements. Suppose I take n equal to 0, I will obtain 2. For n equal to 1, I will obtain 7. So you can see 7 can be obtained by adding 5 to 2. Similarly, we can write the next element by adding 5 to 7, that is 12. Then 12 plus 5, that is 17, and so on. Here we can obtain this element 2 by subtracting 5 from 7. 7 minus 5, that is 2. 2 minus 5 will give us minus 3. minus 3 minus 5 will give us minus 8, minus 8 minus 5 that is minus 13, and so on. Or we can check by taking particular values. Suppose I take n equal to minus 1, this is going to be minus 5 plus 2, that is minus 3. For n equal to minus 2, this will be minus 10 plus 2, that is minus 8. So you can write as you wish. There are different ways of writing the same coset. Then left coset corresponding to the element a equal to 3 is 3 plus h. So I can check whether 3 is present in any of these cosets which we have obtained. Here 3 is absent, here also 3 is absent, and 3 is absent in our subgroup also. So we have to use definition again to obtain this left coset also. So by definition 3 plus h, where h is a member of subgroup, and this is 3 plus elements of h are multiples of 5, that is 5n, n belongs to z, and again we write for particular values of n. For n equal to 0 we obtain 3, for n equal to 1 we obtain 5 plus 3, that is 8, and then I can write by adding 5. 3 plus 5 8, 8 plus 5 13, 13 plus 5 18, and this will continue. For n equal to minus 1 I will have minus 5 plus 3, that is minus 2, and minus 2 can be obtained by subtracting 5 from 3. 3 minus 5, that is minus 2. And the next element in negative direction is minus 2 minus 5, that is minus 7. Minus 7 minus 5, that is minus 12, and so on. So this is the left coset corresponding to element 3. Next we consider 4. So we write left coset corresponding to 4, that is 4 plus h, and we can check whether 4 is present in any of the cosets which we have obtained, and 4 is not present in any of these cosets. So we write this also by definition. This is by definition 4 plus h, where h is a member of the subgroup capital H. Members of subgroup are multiples of 5. So we write 4 plus 5n, where n belongs to z, and we write for n equal to 0 we will have 4, and next element we can obtain by adding 5, that is 4 plus 5 9, 9 plus 5 14, 14 plus 5, that is 19, and in negative direction we subtract 5. 4 minus 5, that is minus 1, minus 1 minus 5 minus 6, minus 6 minus 5 minus 7, and we can check for n equal to minus 1 we will have minus 5 plus 4, that is minus 1. For n equal to minus 2 we will have minus 10 plus 4, that is minus 6. For n equal to minus 3 this is minus 15 plus, for n equal to minus 3 this is minus 15 plus 4, so that is going to be minus 11. Let me check this. So here I have to write minus 11, and we can see that if I subtract my 5 from minus 6, then I also have minus 11. So this is minus 11, not minus 7. So we can check. We subtract 5 from 4, we have 4 minus 5 minus 1, then minus 1 minus 5 minus 6, minus 6 minus 5 minus 11, and in this direction we are adding 5. 4 plus 5 9, 9 plus 5 14, 14 plus 5 19, and suppose I take n equal to 3, I will have 4 plus 5 into 3, that is 4 plus 15, that is 19. So now this is correct. Be careful while writing the elements. So succeeding element can be obtained by adding 5 and previous element can be obtained by subtracting 5. If I want to write down element after this, I will add 5, 14 plus 5, that is 19. And if I want to write down previous element, I will subtract 5 from 14, that is 14 minus 5, which is 9. And in all the left cosets, we can see that this pattern will follow. To write down succeeding element, add 5. To write down previous element, subtract 5. And you can write one element for by taking particular value of n. So if I take n equal to 0 here, I will obtain 1. So I require only one element, then I can write down whole set by adding 5, because difference of any two succeeding elements is always 5 in all these left cosets. Now next one is 5h, that is 5 plus h, and we can see whether 5 is present somewhere or not. 5h, that is 5 plus h, and we can see 5 is present in our subgroup here. This 5 is present here. So 5 is an element of given subgroup, therefore this is equal to h. Okay, we are using this property. If A is an element of H, then left coset corresponding to that element will be subgroup itself. Then next element is 6h, 6 plus h, and we check whether 6 is present in any left coset or not. So 6 is present in this left coset. So because 6 is present in the left coset corresponding to 1, left coset corresponding to 6 will be equal to left coset corresponding to 1. We are using this property that if some element is present in some left coset, that is if A1 is present in the left coset corresponding to element A2, then left cosets corresponding to A1 and A2 are always equal. So using this remark, we can directly write that this is going to be 1 plus h or 1h, because 6 is an element of this left coset 1h. Similarly, we can find out 7 in any of these left cosets. So we observe that 7 is present in the left coset corresponding to 2. So that is going to be 2h, because 7 is present in the left coset corresponding to 2. So 7 belongs to 2h, therefore 7h equal to 2h. Similarly, what about 8h? 8h is present in this element. So we can write that 8h equal to 3h, because 8 belongs to 3h. Now, so we can have idea from this that this up to 4h we started by taking 0. So 0h, then 1h, 0, 1h, 2h, 3h and 4h, and after 4h all these cosets 5h, 6h are equal to any of these previous cosets. So from this we can say that there are only 5 distinct left cosets starting from 0h to 5h, and the cosets corresponding to remaining integers will be equal to any of these 5 cosets. So these are the only 5 left cosets, distinct left cosets of given subgroup. So there are 5 distinct left cosets of H equal to 5Z in a group which is set of integers under addition as listed below. So we have 0h, that is 0 plus h, which is h, then 1h, that we can write as 1 plus h, 2h, that is 2 plus h, 3h, that is 3 plus h, 4h, that is 4 plus h. Okay, fine. So remaining are repeated. So these are the only 5 distinct left cosets of given subgroup H in this group, and remaining left cosets will be equal to any of these left cosets. So these are the only 5 different left cosets of given subgroup. So in this way we can answer this type of questions, but be sure that you don't miss any different left coset. We must write all the possible left cosets which are different, and then we can write that these are the 5 different left cosets. So this is all about this session. I hope you like it. Thank you.